This is the second lecture from Chapter 5, all about gases, and this lecture will introduce the simple gas laws. One of the first gas laws, and one of the more important ones that we're going to talk about, is called Boyle's Law. So at this point, you want to probably have a separate page or a note card with just the gas laws, because by the time we're done with Chapter 5, there will be several, and it'll be a little bit tricky to keep them straight and know which law to use. So here's Boyle's Law. I don't really care that you know it by name. I just care that you know the relationship between pressure and volume. And since the product of pressure times volume of any gas, the variables that are left out, in this case temperature, just means those variables are held constant. And so pressure times volume, whatever that product equals, we'll call it X, never changes, okay? So what that means then is if pressure increases and the product of pressure times volume never changes, what has to happen to volume? Well, for this product to stay the same, if pressure goes up, volume has to go down, and vice versa. So that is an inverse relationship that pressure and volume have. An example of Boyle's Law in our everyday life is actually breathing. I find this fascinating because when you inhale, you aren't doing the work of dragging air into your lungs. All you're doing when you inhale, your body is expanding the volume of your lungs, okay? What happens when you, look at Boyle's Law, what happens when you increase volume, like we just did when we inhaled? When you increase volume, pressure goes down, okay? So by inhaling and expanding your lungs, you've reduced the pressure inside of them, and you've essentially created a vacuum inside your lungs. So as a result of that, air goes rushing into your lungs to fill the vacuum. And similarly, when you exhale, okay? When you exhale, you are compressing the size of your lungs, and in other words, you're making volume go down. If volume goes down, pressure goes up. And what happens when pressure increases? You're going to expel gas or air to equalize the pressure. So anyway, I just think that's kind of an interesting application of Boyle's. On a molecular level, which you will probably be asked to explain, let's look what happens when we change pressure and or volume of a sample. So if you're looking from the left to the right, what have we done? We have decreased the volume, okay? So from Boyle's Law, what happens when you decrease volume? It means that pressure must go up. So if I asked you, explain on a molecular level why pressure goes up, you would give an explanation similar to, well, at a lower volume, the frequency of collisions of the gas molecules with the container wall increases, and as a result, pressure increases. So that's the molecular level description. Graphically, any inverse relationship that you graph, and you've hopefully learned this in math, gives you a downward curving shape. So I'd like you to remember that when you are asked what a graph of Boyle's Law or pressure versus volume looks like, that you would be able to remember the general shape of downward curving, okay? That's a sign of an inverse relationship. Prove it to yourself. Look at the graph. As pressure increases, we have pressure on the y-axis. As pressure increases, what happens to volume? It decreases. Here's an example of a simple Boyle's Law calculation. So let's go ahead and write Boyle's Law up at the top. All right, so go ahead and read the problem. And as you read it, see if you can assign values for what is P1, what is V1, what are we solving for, etc. So let's just call this the first volume we come to, we'll call it V1. Now you have to make sure you put the right volume and pressure together, so read it carefully. 20.5 liters of nitrogen at 25 degrees. Now that's a red herring. You don't need temperature in Boyle's Law. It's not changing, so just ignore it. And 742 torr. Okay, so clearly this volume and this pressure go together. And so we're going to call this P1. Okay, are compressed to 9.8 atmospheres, so that's P2. That's a second pressure we've come across. What is the new volume? So they're asking us to solve for V2. Let's go ahead and plug in all the information we have. 742 torr times 20.5 liters, that's P1, V1, equals P2. Now, I'm hoping that you noticed that P2 is in atmospheres and P1 is in torr. So it doesn't matter what units you have for pressure or volume, but they do need to match. So you need to get very familiar with converting in between torr and atmospheres. So I'm not sure if you remember what 1 atmosphere equals 760 torr. So set up a unit conversion to convert them. So if I have 742 torr and I want to convert it to atmosphere, I'm going to put units of torr on the bottom so they cancel. And I'm trying to get to atmosphere, so that goes on top. And then looking at my conversion, 1 goes in front of atmosphere and 760 goes in front of torr. Cancel my torr. And now 742 divided by 760 will give me my atmosphere. And that comes out to be 0.98 atmosphere. I'm going to go to the next page because I've made a mess of this one so you can see the rest of the calculation. All right, so this is converting between torr and atmosphere again. And number 2 shows all the values plugged in. So here again is P1 times V1 equals P2, and we're trying to solve to V2. Now remember, if you want to solve for something, you have to isolate it. Put it by itself on one side of the equal sign. How do we do that? By dividing both sides by 9.8. Okay? When you do that, you solve that V2 is 2 liters. There is an easier way to do this, and it's probably a simple relationship you should get somewhat familiar with. You can go ahead and calculate the math and find the answer that way. But because pressure and volume are inversely related, I want you to look at how pressure has changed. It's gone from 0.98 to 98. What factor of a change is that? That's a factor of 10 larger. Okay? So volume has to go the exact opposite direction by the same amount. So if pressure increases by a factor of 10, volume must decrease by a factor of 10. So 20.5 divided by 10 means that V2 must equal 2.05 liters. Okay, so with sig figs 2.0. Alrighty, the second law we are going to go over is Charles' Law. Now, again, remember I said the variables that are left out of this equation are held constant. They're not the variables that are changing, and that's why they can be left out. Notice that pressure is left out of Charles' Law. That just means that in order to use Charles' Law, pressure has to be constant. Remember now that you have temperature in here, temperature must be in Kelvin. So if you're given Celsius, you must add 273 to it to get Kelvin. Now, what is the relationship between volume and temperature? In order for volume divided by temperature to stay constant, as volume goes up, in order for this division thing to stay constant, that means that temperature would also have to go up. So that is a direct relationship between volume and temperature. They go in the same direction. So if volume went up by a factor of 10, temperature in Kelvin would also have to go up by a factor of 10. Here's what a graph of Charles' law looks like. It is a direct relationship, and this is a typical graph for any direct relationship. It's linear, okay? As one of them goes up, the other one goes up. Let's make sure that you can explain Charles' law on a molecular level. So imagine you have a balloon, and you blow it up, and you put it in boiling water. The balloon will inflate a bit more than it did at room temperature. And then if you put it in ice water, or even more fun than that, dry ice, the balloon will deflate, okay? The molecular explanation of that is what happens when you increase temperature. Of course, Charles' law tells us that if temperature increases, volume has to increase also. But on a molecular level, you would explain that by saying when you increase temperature, you increase the kinetic energy of the gas particles. They're moving more, faster, more. And so therefore, there are more collisions on the container, which is a balloon in this. And the more collisions you have, the more pressure. So pressure goes up. That is your molecular explanation. Here's an example, and I really should have had you work the Boyle's Law example by yourself. So I would suggest going ahead and turning off the video at this point and seeing if you can solve this problem on your own. There is Charles' Law, and so go ahead and turn it off and check your answer on the next page. Hopefully, you have worked it out on your own first. So I like to go through the problem and assign what V1, T1 is. And let's see, what would the final volume, so they're asking us to solve for V2. They're asking what would the final volume be. And here's the first volume, 247 milliliters. We're going to call that V1. And the temperature that goes with V1 is 22 degrees, so we're going to call that T1. And right now, so I don't forget, I'm going to convert that to Kelvin. So anytime I have Celsius, I'm going to add 273 to it. So my Kelvin temp is 295. That's considered room temperature, by the way. And here's another temperature. This would be T2. I'm going to go ahead and convert that also. So 98 plus 273, 371 Kelvin. So that's T2. Now I'm simply going to plug all these values into Charles' Law and see what I get. All right, so here, oh, can't even see that. I don't know why I put that in black. There we go. All right, so V1 and V2 is what we're trying to solve for. And since you're trying to solve for V2, you have to again make sure that you can rearrange the equation to isolate V2. So that means that we have to multiply both sides of this equation by, what was 98 and 273? 371. We have to multiply both sides of the equation by 371 in order to solve for V2. And we should then get that 311 milliliters. If you have your head about you when you're solving these, you should probably ask yourself the logical question if the answer you got makes sense. Your initial volume of the balloon, or of whatever we're talking about, is 247 milliliters. You heated it up, okay? So what do you expect to happen to the volume? You expect the volume to go up if you heat it up, right? Well, make sure that it did. It went from 247 to 311. Yes, that makes logical sense, so that's just confirmation your answer is probably correct. All right, another law that we're going to talk about is called Avogadro's law. I mentioned that in one of the very first slides in the first lecture. So Avogadro's law is between moles and volume. And now, what are the variables left out of here? There's no pressure, there's no volume. There is volume. There's no pressure and there's no temperature. So pressure and temperature have to be held constant in order to use Avogadro's law. Now, you may remember from the first lecture that in words, Avogadro's law says that if you have equal volumes of any type of gas, those equal volumes contain equal number of molecules, regardless of what the gas is. And so, if you look at this mathematically, volume and moles are directly related, okay? Directly proportional. That means as volume goes up, moles also go up. As volume goes down, moles also goes down. Just as kind of a little side, we'll do that once we get to stoichiometry for gases. 22.4 liters of any gas, as long as you're STP conditions, will contain 1 mole of gas particles. In other words, 6.02 times 10 to the 23rd gas particles. That's only at STP. If you change temperature and pressure, you're going to have different amount of particles and volume. Because Avogadro law shows a directly proportional relationship between moles and volume, you would expect it graphically to be another linear relationship. As one goes up, the other goes up. Here's a problem using Avogadro's law. This one is quite tricky. Well, it can be tricky, and I've seen this type of problem a lot. So I strongly recommend you go ahead and turn this off and make yourself work through it and pay close attention to the wording. And I don't want you to feel bad if you miss it, because there is a little bit of a trick. But challenge yourself, see if you can figure it out, and then I will work it out for you in the next page. Let's go ahead and write Avogadro's law up here. You may already realize this from a mathematical point of view, but it doesn't really matter if you have number of moles on top or volume of top. You're still going to get the same answers. So I want you to go through this question and assign n's and v values. And I will just give you a hint now. That's the trick. So read really carefully, okay? And then turn me off, go to the next page. Now, here's the thing that was a little bit tricky. You might originally think, okay, here's the first mole value I'm coming to. I'm going to call that N1. No, that is not true. N1 is the number of moles that was in the balloon originally. This is what she's adding. So keep on reading, okay? We do know the original volume, so I think it's pretty safe to call that V1. And that balloon, when it was 5.29 liters, contained 2.51 moles of gas. So 2.51 is actually N1, okay? They're asking us to solve for V2. And what is N2? How many moles do I have in there at the end? So if you were savvy enough here, you might figure out the total moles in that balloon at the end were the original moles, 2.51, plus what was added, 3.13, for a total of 5.6 moles, and that is N2. So looking at Avogadro's law and plugging in what we know, we get that the final volume after we add additional moles is 11.89 liters. Does that make sense? Well, it started at 5.29 liters and we added more molecules of gas, so we would expect the volume to go up also, and it did. So, let's see. Let me just put this in real quickly. So, before you rearrange the equation, you'd have 5.9 divided by 2.51 equals, we're trying to solve for V2, and the combined new volume is the new moles is 5.64. Okay, so you're trying to solve for V2, and so you want to get it by itself on one side of the equation, which means we need to multiply both sides by 5.64. And that's how we get 11.89 liters. All right, almost done with the simple gas laws. This is the Gay-Lussac Law. And if you think about the variables we have for gases, so we have moles, volume, pressure, and temperature, we've pretty much combined all of them so far except for Gay-Lussac's, which is pressure and temperature. And so you should be able to answer now, hopefully, after going through the other ones, what is the relationship between pressure and temperature? Anytime you see them in this divided form, it's a direct relationship, okay? As pressure goes up, temperature has to go up in order for this P1 over T1 to stay constant. Here's an example, and as always, see if you can work it out on your own first. Let me go ahead and write Gay-Lussac's law here so that you have it handy. And then I'll solve it on the next page for you. When thinking through how to solve this, let's go ahead and assign values. The volume is a distractor. It doesn't show up in this equation, okay, and it's held constant, which makes sense. A deodorant can is a very hard metal can. That volume is not changing. It's not like a balloon. So we're going to kind of ignore that. All right, so the original pressure is 3.8 atmospheres, and so we'll call that P1. And the original temperature is 22 degrees, which I'm going to call T1. I'm going to right now convert it to Kelvin. So 22 and 273 is 295 Kelvin. That is T1. What is the pressure? So they're asking us to solve for P2 if the can was heated to 100 degrees Celsius, which is 373 Kelvin. So we have all our values, and I want you to think about this. If you have a metal deodorant can, let's say an aerosol can, this is actually a legitimate problem. And if you threw it in a campfire, which is extremely dangerous, I'm going to show you why, from a chemical point of view, why it is so incredibly dangerous, okay? Since you have increased the temperature from 22 to 100, or probably actually higher in a fire, what happens to pressure? Pressure goes way up. And what happens when the pressure gets too high? Kapowie, all right? Those metal cans are made to withstand a certain amount of pressure, but if you throw them in the fire, they're likely to explode, and you basically have a little bomb in your hands. It can be very, very, very dangerous. Hold on, I didn't mean to have that volume there because the volume is constant in the rigid can. So what you get then is the pressure when you increase the temperature to 100 degrees Celsius, the pressure will go up to 4.8 atmospheres, which is more than that container can hold, and you will have an explosion on your hand. All right, now finally, the law I showed on the last page, I meant to wait for this page. There's something called the combined gas law. We're just at the end. Now, this is really important because I'm going to show you how to easily remember all of the gas laws that I just presented in this lecture, very easily. Again, I don't care so much that you remember the names and what law they belong to. I just gave you the names out of respect for the people, but you do need to remember what the laws look like. So, if you remember this one gas law called the combined gas law, P1 times V1 over T1 equals P2 times V2 over T2. If you remember that, you can remember all of the gas laws. Let me show you why. If you have constant volume, whatever you're holding volume, I want you to take it out of this combined gas law. So if we're holding volume constant, we're going to go ahead and take it out. What are you left with when you take out volume? You're left with P over T. Whose law is that? That is Gay-Lussac's law. So now let's check it out for the other one. Let's say instead of holding volume constant, we have a problem that is holding pressure constant. All right, so whatever you're holding constant, you take out of this equation because it's not going to change. And whose law are we left with now? That is Charles' law. And then just one more at the risk of boring you. Let's hold temperature constant. So we will now remove temperature from this equation. And whose law is that? That is Boyle's law. So really all you have to remember is the combined gas law, and it's easy to get the rest of them. So just in case you haven't written all these down, if you want to real quickly to keep them all straight, I guess Avogadro's law is probably the only one you can't get from the combined gas law. So, but by far and away, the combined gas law is the most important one to remember. That's it for this section, second lecture from gases.